Thank you very much, Sergey. I'm very happy to be here, speaking to scientists, it seems, all across Russia in 7 different time zones, I noticed from the webpage. Uh, so yes, I will talk about the old and new work on the long-standing problem of the cuprate pseudogap. And before I start, I should mention my recent collaborators, former student Main Christos, former postdoc Pietro Benetti, Sasha Nikolenko, who's actually from Ukraine, and Avishkar Patel, who's now in Bangalore, and a group of lattice gauge theorists from Chennai. And here are some recent references for more details on things I probably won't get to towards the end. So what I'm going to do, since this is a condensed matter audience, is actually review some key experiments on the cuprates. It's an old field, been around for now nearly 40 years. And, I've been fortunate to watch this development because I started doing physics just when these materials were discovered. But many people have forgotten. So let me just review what I think are some of the key experiments. And this is going on to the present day. The most, I will talk about experiments even from last year. So, of course, this is the famous phase diagram of the cuprates. You start with an antiferromagnet, in which we think of the antiferromagnet as spins on the copper orbitals on a square lattice, which are up and down. And then you remove a fraction p of spins. So this is the axis p. And when you do that, you get the D-wave superconductor. So people always talk about hole doping p, and that would be an important number in everything I'm going to talk about. But it's important to remember it is not the hole density. When we're doing semiconductor physics, or we count holes and electrons relative to filled and empty bands. So in this case, the filled band would have 2 electrons per site. So the actual hole density is 1 plus p, and the actual electron density, which you can just see, is 1 minus p. And these add up to 2 as they showed. Okay, so just remember these key things. So now, one regime where things are very well understood is out here at large p, where there's very little superconductivity. There you see a Hall coefficient of 1 plus p, as you would expect from the filled band picture. And why is it holes and not electrons? Why is the Hall coefficient positive? That has nothing to do with hole doping. It has to do with the shape of the Fermi surface. So this is measured in photo emission, and what you see is that it's the whole area, which is a simple circle, and that's why the hole density, the Hall coefficient is positive of holes 1 plus p. Furthermore, the important Luttinger theorem is very well obeyed. So if you measure areas in units where the area of the square lattice Brillouin zone is 1, then the Luttinger area of this circle is 1 plus p over 2. 1 plus p is the density, and the factor of 2 is for spin, because there's 2 electrons for each momentum state. So that's very simple, and everything works very beautifully. Okay, so now let's go to the opposite end, where you're small p, and there you see Hall coefficient of holes of density p. All right, so that would seem natural if you're in the antiferromagnet, because you can see that the holes are densities p. And indeed, even in the antiferromagnet, things seem perfectly reasonable. This is photo emission experiments on some multi-layer compounds that have different densities on each layer. So for now, just look at the inner IP0 or IP1, which are both in layers which have antiferromagnetism. So you know that these are actually very recent experiments. So this Fermi surface here has, in fact, area p over 4, and I'll explain that in a minute. And that's exactly what, again, Luttinger would say in an antiferromagnet, as long as there's long-range order. So why is it area p over 4? Well, the full Brillouin zone looks something like this. And the antiferromagnetic Brillouin zone is this dashed line. So you have these, it seems like 4 hole pockets, but actually there's only 2 because these 2 are the same as that in the antiferromagnetic Brillouin zone. So there's 2 pockets and 2 for spin. That should give you a degeneracy of 4, and therefore the area of this should be P over 4, and that also works very well. All right, so that's kind of the end of things that work very well in simple standard theory. Now, if you go to the pseudogap, where there is no antiferromagnetism, then you see this very strange Fermi arc. And what that Fermi arc is really what my entire talk is about. This has, of course, been seen earlier in other cuprates, and it's quite a universal phenomenon. You have this strange Fermi arc in intensity when there's no antiferromagnetism in this very important pseudogap area. It's also worth mentioning that this kind of big pseudogap area is very special to the whole doped cuprates. And these are also the materials with still the very best TC. So there's very natural to think that there's some deep connection between the pseudogap and the high TC. So that's one reason we are so focused on trying to understand more about the pseudogap. Okay, so moving on to other experiments, there was a further experiment by the group of Peter Johnson, who claimed to see actually that these arcs were really somehow turning around. And so they boldly said, well, there should be a pocket of this shape. All right, so that's been controversial, although I'm now going to argue that actually they were on the right track. In fact, there were various theoretical proposals for such pockets. There was the famous YRZ ansatz, and then our work that I will say much more about, where the claim was that this pocket should have area P over 8, although it's not seen completely, but that's what we said it should have. And the factor of 8 comes from the fact now there is no antiferromagnetic Brillouin zone, contrary to this picture. And now there are truly 4 pockets and 2 for spin. So that gives you an area of this banana-shaped pocket, which is half the other pocket of P over 8. Okay, this is STM data, which goes across the whole range of densities. And again, you see arcs for small densities and the full original Fermi surface for large densities. And again, they observed that this area, if you just make this crescent shape, just by hand, draw something at the back, that gives you an area close to P over 8. Okay, so then another set of experiments at very low temperatures. The most remarkable was this observation by Louis Taillefer's group in 2007 of quantum oscillations. So these are, I forget, either Subnikov-de Haas or de Haas-van Alphen oscillations. So these are oscillations at high magnetic fields. These are fields of order 60, 70 Tesla, if I remember right, at this doping of around 0.1. And you see oscillations. And from the oscillations, you deduce there's actually a small pocket. But the surprise that no one anticipated is that these are electron pockets. So this is because the Hall coefficient is negative. Okay, so this is giving us very different information that anybody thought should appear in the pseudogap. This is at very high magnetic fields and low temperatures. So there was a proposal by Harrison and Sebastian of trying to understand this electron pocket. And their claim was that there should be some charge density wave acting on the arc. So here's the picture. Here are the bananas I was telling you about earlier. This is the Fermi arc, this front side. And then when you put charge density wave, the other Fermi arcs are shifted by the charge density wave vector. And so then you get this gamma pocket here in the center, which they claim is what's being seen in oscillations. And so some support from this came from later experiments, which in fact do see the charge density wave order. But there's still a problem, which was came up in this calculation. Okay, so of course, Harris and Sebastian only worried about the arcs in the front, but in the underlying system, if not in photo emission, there has to be some backside. In any theory, there's always a backside. So then there's another pocket that's formed by the backsides, this pocket over here, and that should also give you quantum oscillations. And it does in all kinds of calculations, including this one. So that was a problem. That's not seen, that larger backside pocket. But recently, we realized a way to get rid of it, and that required really thinking about fractionalization. So that was when I started to get convinced that there is really strong evidence for fractionalization in the cuprates. But I won't go through this paper because there's even better evidence now, and it's a bit complicated. Okay, then this will be very important for the next set of experiments. There's also observations in a different cuprate, mercury 1201, again at a very similar doping, where you see exactly the same phenomena as in YBCO. So giving you the idea, there's nothing special to YBCO, which has bilayers and chains and a rather complicated structure. This material has a very simple structure, as we'll see in a few minutes. It has exactly the same phenomenology, so it's lending support to this behavior. So what you notice here, and this will be very crucial for what I'm going to talk about now, in the regime where you see these oscillations, the Hall coefficient, which is this axis here, is negative. It's very negative, say again, showing electron pockets. But when you raise the temperature and you go to around 100 Kelvin above TC, it's positive. So it would be really nice to be able to see something up here where the Hall coefficient is positive and the charge density wave order presumably is very weak or non-existent. And that's where recent experiments have been done. So this is this experiment by Brad Ramshaw, which of angle-dependent magnetoresistance. So in this case, you apply a magnetic field at some angle. So this is the Fermi surface of one layer. And then this is because of some C-axis dispersion, you get some warped cylinder. And this is the shape of the orbit of the electrons. And then you vary the angle of B. So this is the angle theta of B. And so the resistance in this direction then varies with the angle. And this is the shape you get. And by solving the Boltzmann equation, you can see you can model it extremely well, at least at overdoping. So no surprise there. But underdoping, this large Fermi surface model fails completely. And what seems to work best is a set of pockets. Okay, this particular experiment is hard to interpret. There's some difficulty, but I think it's basically correct. But finally, I turn to the most recent experiment, which I find the most exciting. So this is in this mercury compound again, at this temperature around 80 Kelvin. And you notice the mercury compound has a very beautiful, simple structure. It's just copper on top of copper. So the C-axis structure is extremely simple, just AA stacking. Whereas in LSCO and YBCO, it's much more complicated. And that complicates the interpretation of angle-dependent magnetoresistance. So they also measured angle-dependent magnetoresistance. They took a model of just small elliptical pockets with this dispersion here. And because of the simple structure in this direction, you just get a cosine dispersion. And what they observed is something called the Yamaji effect, a very beautiful effect, which has been known earlier in other compounds, quasi-two-dimensional compounds. And the effect is the following, that there's a very special angle called the Yamaji angle, at which the area of this orbit is independent of Kz, at least to first order in T-perp. So it requires very small warping. And this area doesn't change very much as you go up and down, which means that effectively there's a flat band in this direction. And therefore the resistance should have a peak at the Yamaji angle. And once you know the angle at which you have that peak, knowing the angle and knowing this spacing, the c-axis spacing, you can read off the area of the Fermi surface just from geometric arguments. So that is exactly what they saw. Here's the Yamaji peak. Here's the full data as a function of theta for different values of phi. Phi is the in-plane angle. And this is the calculation from a simple Boltzmann equation, where really the only input is this dispersion E of k, which I showed you over here. And that simple equation, gives you really perfect agreement with what you see at different angles, all sets of different angles. So this, in fact, is evidence for a whole pocket. It's whole because this experiment is being done over here, where the Hall coefficient is positive. And they also have a very precise measurement of the size of the whole pocket. And that's 1.3% of the Brillouin zone. Okay, I think you can compute in your head what that is in terms of P, but I will keep the suspense for a few more minutes. Okay, so that's the basic story then. There were these Fermi arcs, and then at low temperature, there are electron pockets, which we now understand, we think. And now there's really strong evidence for these hole pockets. And the important point is that these hole pockets do not obey the Luttinger theorem. So what is the theory behind this? So the theory I'm going to now present is what we call the fractionalized Fermi liquid, or FF star. So what is the basic idea? Let's see. Yeah, I think I'll skip that. The basic idea is the following. So in a Fermi liquid, of course, we have the Luttinger theorem from 1960, and also similar results in the Russian literature around the same time, that the area enclosed by the Fermi surface is the same as that for free fermions with the same symmetry. And this is important, say, for the antiferromagnet. If there's some broken symmetry, you should also break it in the free fermion theory, and then you will get the appropriate Luttinger area. So if you have holes of density rho, total density rho, as measured from the filled band, the area should be just rho over 2. So for my purposes, there's an important step made by Oshikawa in the year 2000, which gave the same answer, but from really a much simpler argument. And in fact, the answer here is non-perturbative and more general than this answer, because this really requires some sort of adiabatic continuity to the free fermion system. This makes no such assumption, but it says that it looks at the response of the system to a global flux, say in this torus, in any system that has a global U1 symmetry and has the translational symmetry too. Then there's a certain Berry phase factor that system must pick up, and equating that Berry phase or anomaly to the low energy theory, and assuming the low energy theory has only quasi-particles around a Fermi surface, you get the same answer. Okay, so the Oshikawa approach showed that there's a different way to satisfy the Oshikawa anomaly. You need not obey the Luttinger result, but you always have to obey the Oshikawa result. So what is the different way? Well, it's very simple. You just need some part of your system to be sensitive to flux. It doesn't really have to be a metal with Fermi quasi-particles. So in particular, the system that we now know can do it is some kind of quantized spin liquid with fractionalization. And that has an Oshikawa anomaly of exactly 1. So then the sum of the Fermi surface anomaly and the spin liquid anomaly should add up to the density. And so that tells you that there can be Fermi surfaces which have total area rho minus 1, not rho. So you can subtract. You can't subtract any amount you want. You can only subtract a quantized amount. And the quantized amount is, the simplest case is 1. And so therefore, the total area of Fermi surfaces in this fractionalized Fermi liquid state, which has at least a background spin liquid, if you wish, must be rho minus 1. And therefore, the area per pocket, because factor of 2 for spin, should be P over 8, as I've already mentioned before. So now let me give you a very simple pictorial representation of this kind of state. Well, let's start with the antiferromagnet. So we want to lose the antiferromagnetic order. And of course, the way we do that is by Anderson, Pauling, and I just heard a famous Russian scientist also came up with the idea of a resonating valence bond, where you make local singlets which resonate with each other to give you a state, as we say today, which has long-range quantum entanglement, because it's the coherent superposition of macroscopically distinct states. All right, so now we're going to dope the system by removing some electrons. So remember, I remove this electron here, and that leaves behind a partner spin. Now, what will happen in such a state, naively, and this is about the thinking in the early days, that the spin can move around, and as it moves around, it carries charge 0 and spin 1/2, so it's what we call a spin-on. And the vacancies can also move around, and these what we call holons, which have charge E and spin 0. So the picture is that when you dope an RBB state, you get these deconfined excitations with these strange quantum numbers as your metallic state. Now, if these holons are fermions, then they can give you the temperature-independent Hall coefficient of density P. But there's a problem. They cannot tunnel between layers. So this kind of RBB structure is the same for each layer, but there's no entanglement between successive layers. So if you're measuring the C-axis resistivity, as you measure an ADMR, then the holon cannot tunnel. So the holon cannot be the answer to the ADMR observations, because it can't go from one layer to the next coherently. So what's the answer? Well, the answer is the following. Now, in the ground state, these spins, want to bind up to form singlets, and that will gain you energy J. But you can imagine the following, where the holons, each holon that you have put into the system creates a spin-on at energy J. So that costs you some energy. But now, once you have the spin-on, you can have this resonance like this between the holon and the spin-on, and that gains you energy T. Because that's the hopping matrix element. So that's the very simple, rough argument that, in fact, what will happen is that the holon and spin-on will form bound states. So this bound state has has charge E, as you can see, is one vacancy, and it also has spin 1/2. So it really has the same quantum numbers as the electron, but it's more of an extended object. And then there's the background of singlets. So now the state of the pseudogap, if you want a very crude picture, is just a Fermi gas of the holon spin-on bound states. And there are other pictures by other people, including George Savatsky, which are closely related, where he used the word magnetic polaron. Well, that's completely equivalent to these dimers. And so this is the basic answer at a very crude level of what is the pseudogap. It's just a gas of Fermi gas of holon spin-on bound states in a background of singlets. Okay, so I'm not saying that this is the actual wave function, but this wave function is good enough to allow you to compute the size of the Fermi surface. So what is the Fermi surface you would get from such a state? Well, if these are free electrons, then you have to count every electron. And the number of electrons, of course, is 1 minus P. Or if you wish, the number of holes in a fill band is 1 plus P. So the Luttinger argument for this gas would be 1 plus P over 2 for the area of the Fermi surface. Of course, that's not the correct answer. The correct answer, if you have 4 pockets, is that the area is P over 8. And that comes from counting only the green objects. These are the mobile electrons, which are giving you the Fermi surface. And on the background, if you look at it in a colorblind way, it's just the same old spin liquid, which is making up the deficit of one, because there's one electron per site in the background spin liquid, in the anomaly that appears in the Yoshikawa argument. So let's see. I don't know if that's blocking your view. Okay. All right. So that's that's the basic story. Okay. All right. So now, of course, so this is the key summary, which actually is a figure from this paper in 2007, where we make an important difference between an antiferromagnet, which could be thermally fluctuating, and a quantum spin liquid. There's often a view that we can think of a spin liquid as a fluctuating antiferromagnet, but that's really not correct. It's not correct because if you have an antiferromagnet, then of course we know we get these 4 pockets of area P over 4. Now if this antiferromagnet is thermally fluctuating, you can still use the same picture. And you will still have, that will broaden the Fermi singularity, but it won't change the area of the pockets. So now there's often a view that you can think of a spin liquid as locally as an antiferromagnet. And what I'm saying is that's not correct. You really have to start with the spin liquid on its own terms as a quantum state. And then you will get 4 pockets, because there's no Brillouin zone. And in fact, the center of the pocket need not be centered at pi/2, pi/2, because you haven't broken any symmetry. And that's what we argued in this paper. And therefore, you get 4 pockets, and the area of the pocket will be P over 8. So this is like the key slide of, of the theory here, really. You get pockets that are shifted off the symmetry point and have half the area in a quantum state, whereas in a classical state, they're not shifted. Okay. All right. So now coming back to the Yamaji observation, which said they had 1.3%, and that is actually very close to P over 8, because P is 0.1. That gives you 1.25%. Whereas the thermally fluctuating antiferromagnet would give you P over 4, which is quite far from what is seen. Okay, and there's more detailed calculations in our model in this paper. All right, so that's the, I think that's really bringing together a lot of things about the pseudogap. And, in some ways, we could consider this observation as this factor of 2 difference, as really a smoking gun signal of a spin liquid, because only with the spin liquid could you get the Luttinger violation with this P over 8 area. This AF metal is a Luttinger result. It's not non-Luttinger, because in the broken symmetry state, that's exactly what you get. All right, so now to proceed further, I think I'm doing good on time. Any questions so far, please?
Yes, please.
That's about half my talk.
Yeah. If there are any urgent questions, you can ask right now.
Okay, so then moving on.
Then maybe we'll move on.
Yeah. So now, okay, so this is, so far I have given you just a summary of a whole bunch of experiments and some very simple hand-waving arguments, which actually help us understand the key features of the experiments. But we'd like to do, of course, better. And so for now, we need a real theory. And for that, we need a theory of the spin liquid. Because if this picture is correct, then you really have to start from a spin liquid to understand the pseudogap, and presumably also the superconductivity. So the second main message is that the simple resonating valence bond picture of nearest neighbor singlets is not the correct picture. And what's happened in the last 30 plus years is that through a variety of analytical and numerical studies, we have a much better understanding of what is an spin liquid on the square lattice actually look like. So that's kind of what I want to talk about now, is to review in a brief manner some of that work. So now we'll, just to begin with, all of that work has been on insulators. And our more recent work is to take this modern understanding of insulating spin liquids and apply it to the pseudogap. But let's just first talk about insulators. If you want a specific model in mind, just take this very simple model, which many people have studied, but there are other models that have very similar properties. We have spinor halves on each side of the square lattice with nearest neighbor exchange J1 and diagonal exchange J2. Now in the cuprates, J2 is very small, and when only J1 is non-zero, then you have nails, the antiferromagnetic state that I've shown you. So the question many people have asked is, now you turn on J2 and increase it. What is the spin liquid state that you will reach? Okay, so I'm going to now answer that question, since based on a lot of people's work. So one work which was quite successful is this work that I did with Nick Reed way back when. And this, we represented the spin in terms of these bosonic partons, which carry spin a half. So when you make this representation, you introduce a U1 gauge symmetry, because that doesn't change any physical operator. And therefore, the effective theory in this representation is a gauge theory. And now, a lot is understood about the structure of this gauge theory. So if you take the low energy limit, you just get a U1 gauge theory of complex spinors, which are closely related to these B alpha. That's called the CP1 field theory. Relativistic, in fact, it's relativistic and has two complex scalars. Okay, but that's not the whole story. Because you're on a lattice, you can also get monopole events in this 2+1 dimensional gauge theory, which Polyakov studied in his famous work on compact electrodynamics in 2+1 dimension. But in this case, because there's also some matter fields around, you get extra Berry phases associated with the monopoles. And these Berry phases are closely connected to this Lipschutz-Mattis anomaly and the Oshikawa anomaly. They're all very much related to the fact that you have spin a half for each side of the antiferromagnet. So anyway, this theory has been studied thoroughly now. And the prediction is that there is a transition from the nail state, where these spin-ons are condensed, to a spin liquid-like state, where, however, because of the Polyakov mechanism, the monopole condensation leads to this valence bond solid order, but at a rather long length scale. So near the phase transition, which in fact is nearly critical or exactly critical, depending on whose simulation you look at, and really quite a bit distance away from it, it's a critical spin liquid, which is described by a conformal gauge theory. All right, so this is the picture that's been developed of the square lattice spin liquid. And as I mentioned, there's a lot of numerical work which now supports the predictions that were made from the analytical work. But people say, okay, that's great, but what is this to do with high TC? And so I would have no answer when people ask me that question until a few years ago. So another line of thought for spin liquids on the square lattice actually goes back already to early work of Anderson, where instead of using bosons for the spin-on, for the spins, they used fermions, which are also equally valid to begin with. So in this case, if you look at the saddle point, and many different saddle points have been studied, but the appropriate one we know today is the so-called pi flux saddle point. So these spin-ons move on the square lattice with a fixed background flux of pi per plaquette. That we know today is the best saddle point. And then if you look at the dispersion of the spinon, just diagonalize this, it's very much like graphene. You get two valleys of massless Dirac particles. So whereas in graphene, the particles carry spin and charge, here they only carry spin and a half. So that's why they're spin-ons, near neutral spin-ons. All right. Now, in any such parton theory, there has to be an emergent gauge field. And in this case, oh, sorry, before I go there. So that's great. You got a very different state. But this state was not seen in any numerical study. So it wasn't very clear what this is all about. But what was already clear from the early days in these papers is that if you dope the system, we will naturally get the D-wave superconductor. So this is kind of where things stood for quite a while. You have a theory of spin liquid that works well, but doesn't give you superconductivity when you dope it. But there's another theory that does not seem to work very well, but does give you D-wave superconductivity. And that's been the stumbling block for many years. But now that has been cleared up because of some very beautiful work. So people thought more about what are the fluctuations about this pi flux state. And it's been known that the fluctuations now are described by an SU2 gauge theory, where U is some lattice SU2 gauge field. And in the continuum, this just couples minimally to these Dirac spin-ons. So this is the low energy theory, and it's very, very similar to the theory of light quarks. So that's the theory of light quarks is an SU3 gauge theory in 3+1 dimension with 3 flavors of light quarks. And he just replaced all the 3s by 2s. This is a theory in 2+1 dimension with 2 flavors of light spin-ons and an SU2 gauge field. Now, just like in QCD, where people now understand the confining phases of QCD, here also we've started to understand what are the confining phases of this theory. And amazingly, they turn out to be exactly the states that were seen in the bosonic spin-on partition, the Néel state and the valence bond solid. So this is the modern understanding of this theory. It gives you, in fact, the same phase diagram as the bosonic spin-on theory. And in some formal sense, as discussed in this paper, there's a duality. So now this is great. You have this dual descriptions of the same spin liquid. And this particular spin liquid, this representation with fermionic spin-ons, also allows you to get superconductivity. So now we know what to do. This is the correct spin liquid, as we know from numerical studies. And it also gives you D-wave superconductivity. So that's also then a nice confirmation of the old idea that spin liquids are really important for high temperature superconductivity. All right, so let's now finally get to the recent work. I'm now going to dope this particular spin liquid. So the way I'm going to, so we're going to start from the pseudogap and ask, how do you get the D-wave superconductor? Well, there is a theory of D-wave pairing that starts from the Fermi liquid, where you just start with the BCS approach, and much like in helium-3, you put in spin fluctuations, in this case, antiferromagnetic spin fluctuations, and that's been long known to give you D-wave superconductivity. And that's perfectly fine, I believe, when you're in this high doping site, because the starting point works. The starting point of BCS theory is the Fermi liquid. But now that starting point cannot be applied because we think we know what the theory of the pseudogap is. Theory of the pseudogap is FL star with a pi flux spin liquid. And now to get superconductivity, we have to somehow get rid of the spin liquid character. We have to get rid of the spin-ons, which are not exactly the same as Bogoliubov quasi-particles because they carry a gate charge. All right, so the constraint that a theory must obey from a lot of experiments, which the theory does obey, is that the superconducting state itself is not exotic. Well, the pseudogap is exotic. The state that you get in the sense of low energy theory is the same as the state you will get here. In particular, this state has 4 Bogoliubov gapless quasiparticles, and this state should have the same number. And that's what we find in our theory. But there is a difference. There's a difference in the structure of the vortex core. So if you do the theory in this approach and look at what happens in the core of the vortex, the Abrikos of vortices, you get what's sometimes called the Van McDonald peak. That has to do with the nodal quasiparticles interacting with the states in the vortex core. And that is seen at high doping. But at low doping, the core is very different. You don't see this peak at all. And that also comes out actually from this theory. So the FL star vortex core and the superconductivity vortex cores are very distinct. All right, so now let me just say a few words of the actual theory and how everything comes together. All right, so this is the key idea. So to obtain nail order from the pi flux spin liquid in the insulator, we confine the spin-on, similar to quarks in quantum chromodynamics. But to obtain D-wave superconductivity by confining the spin liquid, we will use a Higgs field. And now this is similar to the theory of electroweak interactions. It's kind of remarkable how we're using the same old tricks that are used in the standard model. So we introduce, and there's of course a way to do this from a microscopic derivation, but I'll present it as if we could just have figured this out just by symmetry. So you introduce a SU2 fundamental Higgs boson. It has to be SU2 fundamental because only then its condensation will completely confine the SU2 gauge field, which is the case also in the theory of electroweak interactions. And we also introduce a charge, and they also carry a charge E. That's also the case here, because that will allow us to get superconductivity. Okay, so once you have this, you have now 2 SU2 fundamental fields. One is the boson B and the spin-on F. And then you require that the product of the two, just like the green dimers, the composite bound state of the two should give you an electron. And that's really all you need to know. So knowing that, we can write down a Landau theory. We need to know all the symmetries. And in this case, we also have the gauge symmetries, and that introduces a fundamental difference. That whereas the usual Landau theory is invariant under all symmetries, the gauge theory is only invariant up to a gauge transformation. So this is the key thing that you have to figure out. What are the gauge transformations of the B and the F under the square lattice and other symmetries? But you know the symmetries of F because from the pi flux ansatz. You know the symmetry of E, that's just an electron. And so that because of this composite relationship, you can deduce the symmetries of B. And that's enough. So now you get some Landau action, you minimize it, and you look at, to physically interpret the different minima, you must look at gauge invariant observables. So that's the task. And, looking back at it, it looks very straightforward, but surprisingly, it wasn't done for the simplest spin liquid on the square lattice until this paper. And so let me just tell you, it's a relatively straightforward thing once you have the right idea. And let me just tell you some of the things that come out. So in particular, just from knowing these symmetries, you can write down different gauge invariant autoparameters using the Higgs boson. So there's a pairing autoparameter on each bond. There's a site density, there's a bond density, there's a bond current. So just by computing these quantities here in the Landau theory, you can deduce what the state is. So what do you get? Well, so this is the free energy. I won't go through the various terms to up to quartic order. The most important term is this coupling R. And when R is positive, you don't have a Higgs condensate as in usual Landau theory. When R is negative, then you have a condensate. Okay, so as a function of R, when it's positive, then there's no condensate. And then you get the FF star state with the pi flux spin liquid, which would then confine at low temperature to the Néel state. And when R is negative, you can get a variety of phases depending on these higher order Landau couplings. And in particular, you can choose parameters that you see exactly the phases that are seen in the cuprates. That includes, in particular, D-wave superconductivity. Now, it might seem that you can put anything you want in this rather very general theory, but it's not true. You never get an S-wave superconductor, for example. You get precisely a D-wave superconductor. And it's also relatively easy to get the strike state. But there's a few others that I won't talk about. So this is the theory now that we have. We have this Landau theory. So far, we've just minimized it. And so now all we have done to begin with is put in thermal fluctuations. So this is the work with the lattice gauge theorists. So you just take this Landau energy functional, and then you integrate over the SU2 gauge field and the Higgs field at a temperature T. So just classical thermal fluctuations. So this is the analog of if you were doing BCS theory, you would say, well, at low energies, it's just the XY autoparameter. So you would do thermal fluctuations of the XY autoparameter and get a costless Thouless transition. Berezinski costless Thouless transition. So that's exactly what we're doing here, except we have a gauge theory. You have an SU2 gauge theory with a Higgs field and an SU2 gauge field. So it's quite a bit more complicated to simulate, but with the help of the lattice gauge theories, we succeeded in doing it. So here's a low energy snapshot of this static configuration of the gauge fields and the Higgs field. And if you look at the gauge invariant quantities, in this case, the phase of the usual pairing amplitude, you'll see these vortices here. And this is the bond density for each vortex. And so you notice for everywhere there's a vortex, there's some structure in the bond density. And if you zoom in, you see this period 4 modulations. That period 4 is, of course, chosen by our parameters. But it's very, very natural for the vortex core to be very different from BCS theory here. So at long distances, it's precisely the BCS vortices, which have flux h over 2e. And that's actually quite significant because the bar boson has charge E. So you might think you will get only flux h over E, but because of the SU2 gauge field, you can actually get flux h over 2E. And those are the lowest energy states. So that's what you see. And this is, of course, suggestively similar to what's seen in scanning internal microscopy in the underdoped region of the cuprate. So there's a strong disagreement in the vortex structure from BCS theory in the vortex core. And we don't fully understand what's going on here, but we think we are pretty close. All right, finally, I'm moving well. I have a few more minutes. Finally, what about these Fermi arcs, which you're seen in photo emission? So that's going to, that's the missing piece of the theory. I've assumed so far that there are these hole pockets. So what we're going to do, so for that, we need a theory of how to combine. So you have to couple this SU2 gauge theory to the fermionic spin-ons and to the hole pockets. So again, that can be done just by symmetry. Just the way I've outlined. So if you wish, so far I've done the Landau theory of superconductivity. And now I'm going to do the Gorkov theory, which includes the fermions of superconductivity coming from a pseudogap. So you have the fermionic spin-ons coupled to the same SU2 gauge field. And then you also need the hole pockets, which are bound states of spin-ons and holons. So in fact, it turns out that the better way to obtain the fermionic, the hole pockets is by starting with the full electrons and hybridizing with a band of spin-ons. And that gives you exactly the right size of the hole pockets. So you might think this is too much. You have these spin-ons F, and then you have another set of spin-ons F1 to form the hole pocket. But that's really actually a key point. You can add to any model, you can add a set of two bands of spin-ons with some high energy states, because two bands are smoothly connected to a band insulator. And in fact, precisely the bound states of these two spin-ons and F and S1 spin-ons are what give you the paramagnons in the overdoped side. Okay, and then finally you can use symmetries to couple everything together. All right, I realize that's a bit mysterious. There's a way to do this microscopically, which I won't go into, but you can read about in various papers. You can start with a Hubbard model and just add a decoupled set of spins, which form a trivial spin ladder compound with this trivial ground state. It's very important that you add something with a trivial state. Then by canonical transformation, you can write it down in the way I've been describing. You have electrons and the band of spin-ons F1 here and the band of spin-ons S2 here. Okay, so I'm sorry, I don't have time to go into the details. They're a little technical. But in the end, either by using this Ancilla method or just using symmetry arguments, you can write down some effective theory for the fermions and the bosons in the pseudogap. This is the full theory, but I won't spend any time on it. So now what we do is we do kind of a Born-Oppenheimer procedure, which again, many people have done for the BCS theory. So in the BCS theory, you take an XY model, you do some thermal simulation, and for each snapshot of the XY field, you diagonalize the Bogleubov-Dujan Hamiltonian of the fermions. So we do exactly the same here, but for a gauge theory. We simulate the classical gauge theory, and then for each snapshot of the gauge theory, we diagonalize this ancilla fermion Hamiltonian. So from that, for example, if we start out, we have the four spin-ons and the hole pockets in the mean field theory, and you put in the coupling from the Higgs field between the spin-ons and the electrons, and that gives you exactly the arcs, which we think are quite similar to what's seen in this Monte Carlo simulation. And at the same time, you can ask, do these fluctuations destroy the Yamaji effect? Well, unfortunately, that's too hard for us. We haven't done that calculation. But we did compute for these thermally fluctuating state, the oscillations in high magnetic field of the density of states. And we see that there are definitely regimes where there's essentially no backside observable, but nevertheless, there's oscillations, at least at high fields. Okay, so that's basically the end of my talk. So the basic punchline is that I believe there's a lot of evidence now that the pseudogap metal is a fractionalized Fermi liquid. So this is the very simple picture of it. And then you can think of it as a Fermi gas of holon spin-on bound states, and this explains the pockets seen in various magnetotransport experiments. And then coming from the pseudogap, the more precise theory is that of a pi flux spin liquid. And this connects very nicely to the low temperature D wave superconducting state, giving you the same state as in BCS theory, but with different vortex cores. So thank you very much. And again, I show the pictures of my collaborators.